Okay, last 2 pages in our Unit 2 homework packet, pages 10 and 11. Let's look at this one. Is this an image of fission or fusion, and how did you know? So in my class, I taught students fission division, okay, or look at your S's. So F-I-S-S-I-O-N versus F-U-S. So if there are 2 S's, that's because there are 2 things at the end. So I see S, S, 2 S's. This would be fission division. How did I know? Because there are 2 things at the end. There are 2 products. Okay. Fusion would look more like this. There's 1 product at the end. So 1 S in my answer. 9, 10, and 11, comparing fission versus fusion. Number 8 says the reaction that occurs within stars. Main sequence stars do hydrogen fusion, turning hydrogen into helium. Okay, other stars still do fusion, but they'll do of heavier element fusion. Number 9, the reaction used in nuclear power plants. So on Earth, our nuclear reactions are primarily fission reactions. We use something big like plutonium or uranium or thorium, and we break it up into smaller things, dividing it, fission division. Number 10 produces lots of dangerous waste byproducts. There's some radiation from both, but primarily this is fission. Fusion's products are generally pretty stable. Fission's the dangerous one. And then 11, fission or fusion requires extremely high temperature and pressure to occur. Both of them do, but fusion is so much more temperature and so much more pressure. That's why we have to do fission on Earth. It's easier for us. It's more effective for us. Fusion is harder to sustain on Earth, which is our answer for number 13. So on number 13, it said, describe the process of fusion and explain why we're unable to use it on Earth as a source of energy at this time in 3 or more sentences. So I said fusion is when 2 nuclei are combined. It requires very high temperatures and pressures to sustain fusion. On Earth, it isn't effective to maintain those conditions. Excuse me. Let's look at the next page. This is what we've covered in class today, our new stuff, the electromagnetic spectrum. So I gave you the EMS, the electromagnetic spectrum up here, and what I would do on a test or a quiz or homework assignment is write down some really simple answers. So the first thing, if we look at number 2, it says which one has the greatest frequency. Frequency is how frequent, how common, does it repeat, is it repetitive? So here it's not as frequent compared to here. You're seeing like the up and down. So over here I'm going to write highest frequency, and here lowest frequency. So which wave above has the greatest frequency? Radio, micro, infrared, visible, ultraviolet, X-ray, gamma ray. Well, the greatest frequency is here, so I'd say gamma. The other thing I would look at would be wavelength. Excuse me. Wavelength. The length of the wave. So here, where a wave repeats itself, that's a pretty long wave, versus over here we're looking at much shorter waves. So here I'm going to say small wavelength. Over here I'm going to say high wavelength. And you'll notice those are opposites. For number 3, it says, which one do you predict to have the greatest energy? For waves, energy is equal to frequency. So I'm going to say this is also highest energy, and if this is lowest frequency, this is lowest energy. So the greatest energy, are radio waves more dangerous or are gamma waves more dangerous, like gamma radiation? Well, yeah, gamma rays are going to be our most dangerous because they have the greatest energy. So that leads us to our number 4 answer. Energy and frequency have what kind of relationship? This is the greatest frequency and the greatest energy. So they are up together or down together. They go in the same direction, which means they are a direct relationship. Okay. Number 8. Which of these types of electromagnetic radiation has the longest wavelength and carries the least amount of energy? So I would say infrared light right here, A, visible light, B, X-rays, C, microwaves, D. Which one has the longest wavelength? Radio waves is the longest wavelength, which means the least energy. So microwaves, longest. Frequency and blank have an inverse relationship. So inverse means inverted or upside down. So that's when one is big, the other is small. So do frequency and color have an inverse relationship? But that's not even, I don't even understand that. That's, no, garbage. Take it out. Frequency and energy have an inverse relationship. Do they go in opposite directions? Frequency and energy. I already wrote this down for myself on my test or quiz. See how smart that was? Okay. No, they're going down together. They're not inverted. They're the same direction. So no. Frequency and wavelength. Well, frequency is down, wave is up here. Frequency is up and wave is down there. So those are inverted. They're upside down. That looks good. And then frequency and speed. Speed of light is constant for all of these. They all move at the same speed. So I can get rid of bye-bye speed. So yes, my answer would be wavelength. Frequency and wavelength have an opposite inverse relationship. Number 10. Which of the following is true of all kinds of electromagnetic radiation? They all have the same wavelength. Do they? Big? No, they definitely don't. This graph, this table clearly shows me they do not have the same wavelength, nor do they have the same frequency, right? Repetitive, not as repetitive. Frequent, not as frequent. So that's not the same. They all travel at the same speed, maybe. They all have the same color. Well, this would be like purple. This would be like red. These ones don't even have color to our eyes. So no. C is our answer. They all travel at the speed of light. Okay. Then 11 looks way more intense than it really is. Okay, let's circle our qualifying information. It says a certain wave is found to have a wavelength of 600 nanometers and a frequency of 500 T hertz. I don't even remember what T stands for, so we'll just call it hertz. All right. What color do you expect? So this is my reference table. I'm going to find those two values and see what color it is. So here they're saying wavelength. So 600 nanometers, nm, would fall right here. 600 is between those two numbers. Okay. And then 500 hertz, terahertz, there it is, terahertz. 500 would be between these two numbers. So that makes them both orange. Okay. We're just trying to get you reading graphs, reading tables. I'm just trying to find those two values and match it up to the color. All right. Good job, y'all.